Hello, everybody. My name is Philipp Ginal. I'm a PhD student at Zoological Research Museum in Bonn, which is part of the LIB now. And I want to present you a part of my PhD thesis concerning mechanistic SDMs and connectivity models with focus on the African clawed frog. And for mechanistic SDMs, so species distribution models and connectivity models, scientific databases and collections are very important because they are the basis and allow to recognize changes. Further, it is also very important to understand the concept of the ecological niche. The ecological niche is comprised by the fundamental niche, which represents all the abiotic factors that are relevant for species persistence, the biotic interactions. So for example, predator-prey relationships, parasitism, and so on, and the geographic accessibility. And the interplay among all the three is called the realized niche. And the realized niche can be seen in geographic space, but it also can be seen in environmental space. So as an n-dimensional plot, which comprises all the relevant variables. Yeah, this is Xenopus laevis, the African clawed frog. Xenopus is native to sub-Saharan Africa. But it was distributed all around the world, and now you can find it on 5 different continents. So you can find it in Africa, in North America, in South America, in Asia, and in Europe. And in Europe, you can find it in Sicily, France, and Portugal. And Xenopus has some very interesting characteristics that makes it a very successful invader. For example, females can lay up to 10,000 eggs. Then the species can tolerate a high variation of different environmental conditions. For example, a high level of salinity, a high variation of pH level. It can persist during droughts because it burrows into the ground. It can survive for several months without food, and so on. And this is the reason why in the past several approaches tried to predict the potential distribution for Xenopus in Europe. And here you can see different correlative approaches. And these correlative approaches all link geographic occurrences with environmental data. And here you can see these predictions all predict very different areas as suitable. And this is because they use different algorithms. Here, for example, max-end, hypervolumes, ensemble, and they also use different predictors. But all these correlative approaches have the disadvantage that they only can reflect the realized niche of a species, but not the real physiological constraints. And this is the reason why we calculated the first mechanistic SDM for Xenopus, and for this, we assessed different performances under different temperature levels, and we also included the critical thermal minimum and critical thermal maximum, so the thresholds to death. And then we get these very nice performance curves where you can see the minimum, maximum, and of course the optimum. And here you can see it for adult frogs and tadpoles, which is also an advantage of mechanistic SDMs, because you can include different life history stages, which is not possible for correlative approaches. You also can include local adaptation, which is also an advantage. Here for Xenopus, we included 2 populations from the native range in South Africa and 1 invasive population from France, and the French population derives from the 2 populations in South Africa. And we found that the French population performs under much better under cooler conditions. So it already adapted to the much cooler climate there. Then the next step is that we translated these 2-dimensional plot into a 3-dimensional plot. And at least for the adult frogs, we could include the size as a variable. And then we translate this thermal performance curve into geographic space. Here we have it for different performance variables, for maximum velocity, acceleration, endurance time, endurance distance, evaporative water loss, standard metabolic rate. And we also included the hours of activity and the hours of restriction. And the hours of activity is the daytime when temperature allows performance, and the hours of restrictions is the daytime when performance is not allowed. And it was shown that including these is a much better predictor. And here we have the results of our mechanistic models, here for adult frogs, for tadpoles, and for both together. And we've predicted, or the prediction for South Africa fits quite well to the real distribution of the species, which is a very good sign. And for Europe, we predicted that especially the Mediterranean and oceanic climate zones are very suitable for Xenopus. And we found that almost 2 million square kilometers provide suitable climatic conditions in Europe, which is almost twice of the maximum predictions from the correlative approaches. And now we come from a more global scale to a more local scale. Before we had a resolution of around 5 kilometers per grid cell. Here we have a resolution of around 5 meters per grid cell. Here we are in Portugal, where Xenopus is also found and invasive. And you can find it in 2 different rivers, in Laje and Barcarena. And these rivers are connected, but the populations are not connected. And despite Xenopus is a predominantly aquatic frog, we know that it can move overland for 2.5 kilometers to reach distant water bodies. And the purpose of our work was to reconstruct the terrestrial dispersal route and to identify areas that are suitable for future invasion. And for this, we use a novel approach. And this novel approach bases on satellite images, which comprise 5 different wavelength channels. So red, green, blue, red edge, and near infrared. Then we did some necessary corrections for the further processing to calculate our resistance surface. And for this, we calculated the NDVI, a vegetation index, and the NDWI, a vegetation index that also includes the water content of the vegetation, because we assumed that a predominantly aquatic frog would prefer moist vegetation when it moves over land. Then we scaled our resistance surface to values between 0 and 1. And based on the best matching threshold, which we identified by manual comparison with real images, we identified human buildings. And the purpose was that we could assign specific values to semi-permeable structures like screeds, and which, for example, could be crossed for a certain distance, or another specific threshold to buildings, which are real barriers, which couldn't be crossed by Xenopus. And together with the elevation layer and the confirmed occurrences, we used the remote sensing derived resistance surface to calculate our resistance kernels. And we used these kernels to check the accessibility of the water bodies. And here you can see our results. First, we here have the identification of routes into other regions which are could be invaded by Xenopus, and indeed we found some, and this knowledge can be used to block these corridors to hamper the further spread of Xenopus. And second, we also could reconstruct the past dispersal route of Xenopus, and between the 2 rivers we found only 1 suitable corridor, and this corridor provides 3 golf course ponds. And we know from field data that Xenopus is found in these golf course ponds. So it is very likely that it used these ponds as stepping stones to reach the Barcarena River. So yeah, thanks for your attention, and I hope I could tell you some interesting stuff about mechanistic SDMs and about connectivity models. And if you have further questions, please contact me.